Hi viewers, welcome to all. Here we are discussing about a project, a configurable floating point multiple precision processing element for HPC and AI converged computing. There is a growing need for applications in a high performance computing and artificial intelligence that require programmable accelerator with varying degree of accuracy. Okay, because of this, the floating point processing element, which is the most fundamental component of the accelerators, is required in order to fulfill multiple precision requirement while maintaining an efficient use of energy. However, the proposed structures that uses a high precision split and low precision combinations approaches both results in a lengthy multiplier processing duration and low usage rate of the multiplication array. A programmable floating point multi-precision processing element architecture utilizing the low precision combination structures is presented as a potential solutions in the article. There is a support of a half precision, a single precision and a double precision method. It's utilizing segmented multiplications regarding help to improve the functionality of multi-precision floating point multiplier in 16-bit, 32-bit and 64-bit respectively. The innovation architecture of multi-precision model design, which makes a double output DO, RCA and CSA forced to compressor and parallel full adders and parallel half adder. This work was built in Verilog HDLs, validated with modulism, synthesized with Xilinx Vertex 5 FPGA and compare all the parameters in terms of area, delay and power. Now we can verify the base paper. So this is a base paper title, a configure floating point multiple precision processing element for HPC and AI converged computing. Okay, HPC means high performance computing. Okay, AI means it's artificial intelligence. Okay, so here they are designing a floating point multi precision method. That means a floating point multiplier with a multi precision. Okay, here what is meant by multi precision means here 16-bit means it's a half precision and 32-bit means it's a single precision and 64-bit means it's a double precision and 128-bit means it's a quadruple precision. Okay, so based upon the bit size, okay, it will be decided it's a precision, okay, single or half. Okay, so overall all the combinations of three things, okay, here they are planned with the three things. One is a 16-bit, 32-bit and 64-bit. They are developed here. Okay, so that they are used this work as a multi-precision processing element. Okay, now we can verify the depth of the work. Here this is a proposed architecture. Okay, figure 4 it will be shown. Okay, so initially they are given as a 160-bit, 160 input bit. Okay, input A and input B and mode 1 down to 0. Okay, and it will be given into the input pre-processing. Okay, then after input register. Okay, so this input pre-processing will split the input from the input A and input B. What it will be splitted means it will be splitted sine, exponent, mantissa and control. Okay, so based upon these things, okay, it will be splitted. Okay, so how much bit it will be splitted means sine, exponent, mantissa. Okay, they are given on here. Okay, so here you can check what is the bit size of sine and what is the bit size of exponent and mantissa. Okay, so here half precision, single precision, double precision. Okay, so half precision means one is a sine bit. Okay, and 5-bit is a exponent and 10-bit is a mantissa. Okay, single precision means one is a sine bit, 8 is a exponent and 23 is a mantissa. Double precision means one is a sine bit and 11 is a exponent and 52 is a mantissa. Okay, so based upon these things, the input register will split the value on here. Okay, after that it will be stored into the sign processing, exponent comparison and multiplier array. Okay, so here sign processing means it's a simple XOR operations and exponent comparison means it's a addition process. Okay, additions with subtractions. Okay, we need to subtract with the bias value. Okay, so based upon that it will be happen. Okay, exponent comparisons. Okay, and this is a multiplier array. Okay, so multiplier array means we need to multiply the two mantissa value, okay, A value and B value. For that we are using the multiplier array on here. Okay, after that it will become on the alignment shifter and adder tree. Okay, so alignment shifter we are used for the exponent and mantissa value we need to align with here. Okay, and this is a added 3 and CSLA operator to add the value of incrementation 1 from the exponent comparisons. Okay, and after that we are given the data to exponent normalizations and mantissa normalizations, and finally we are taken the value. Okay, so this is a overall architecture. Okay, but here they are used 16-bit, 32-bit and 64-bit also. Okay, how they are controlled this 16, 32 and 64 means using this control signal and mode value. Okay, so here the mode equal to 00 means, okay, FP16 floating point 16. Okay, mode equal to 01 means FP32 and mode equal to 10 means FP64. Okay, so based upon this mode selection, the multiplication will provide the output. Okay, but here the challenging position is here each multiplier, that means 64-bit, 32-bit, 16-bit means each multiplier will occur in different sizes. Okay, so based upon the sizes we need to manage with on here. Okay, now we can verify the depth of the base paper. Okay, so here this is a overall top model architecture, and so this is a next level of architecture, figure 5. Okay, so the partitioning method of FP32 and 64. Okay, so why they are given this bits means, okay, so here once they are splitted the value multiplier, the multiplication value we are splitted, right. Here multiplication value splitted value is the mantissa equal to 10-bit, okay, for FP16, and the mantissa equal to 23-bit. Okay, so once you are splitted the value 23 bits, here they are added with 1 bit additionally. Okay, and taken it's a 24-bit, so that 24-bit they are splitted into 12-bit. Okay, and the mantissa of FP64 it will take a 53-bit. Okay, so that bit size they are splitted with a 5-bit, 12-bit, 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 12-bit. Okay, so A0, A1, A2, A3 and A4. Okay, so once the 12-bit will be splitted, it will given into the 12 cross 12 multiplications. Okay, that's why they are splitted that bit on 12-bit size. Okay, that 12-bit multiplications they are given on here. Okay, so this is a 12-bit multiplication process. Okay, so operand A, operand B, operand C, okay, they are given A equal to 12-bit cross 12-bit operations, and B equal to 12-bit cross 5-bit operations, and C equal to 12-bit cross 5-bit and 17-bit cross 5-bit operations of multiplication they are used. Okay, here this addition process for this multiplication they are used a 4:2 compressor and 3:2 compressor and accumulation part. Okay, so this compressor part they are given on here. Okay, so this is a compressor for 4:2 with a 4 CSA method. Okay, so this is one of the addition process. Okay, so here the mantissa multiplication for 16-bit and 32-bit and 64-bit we need to handle with the segmentation method of multiplication. This is one of the segmentation method. This is for 64-bit. Okay, so here once we have splitted the value of A0, B0, A1, B1. Okay, after that we need to given the input on here. Okay, A3 into B0, A2 into B1, A1 into B2, A0 into B3. Okay, so based upon the splitted segmented multiplications we need to design it, and we will take the output on the final stage with a sum 1 and sum 2. Okay, so this multiplication process and addition process for this multiplication they are used the architecture here. Okay, figure 9 and figure 12 and figure 13. Okay, they have overcome the ripple carry adder from the carry salter adder existing method. Okay, and they are design a new one. Okay, it's a DO RCA. Okay, double output RCA. Okay, to reduce the number of RCA in the existing method. Okay, and additionally in the paper PFA and PHA, that means a parallel full adder and parallel half adder. Okay, this is the architecture for parallel full adder and parallel half adder. So we are using this parallel full adder and parallel half adder in the RCA. Okay, and after that we need to develop the CSLA architecture, and this CSLA architecture and this RCA and full adders we are used on the multiplication part, and this multiplication part we are used in the top model of the architecture. Okay, so this is a overall process of the work. Okay, now we can verify the coding of this work. Okay, so here we are developed a 2 level of coding. So one level of coding, we are not used any multiplications, any addition from the paper. Okay, we are used as a basic addition, that means operator based multiplication and addition we are used. Okay, why? Because we need to check the accuracy of the multiplication. Okay, that's why we can say it's a multi precision one. Okay, and second level of the coding, we have to shown it's used with this paper architecture of multiplications and addition part. Okay, so here this is the coding for HPC method. Okay, that means the paper based multiplications method. Okay, so this is a coding. So this is a test bench of the coding. So here we are given 16-bit, 32-bit and 64-bit also. Okay, this is a mode value. So once you are given the mode 00 means, okay, it's working on half precision, 01 means single precision, and 10 means it's a double precision. Okay, so based upon this input configurations it will be work. Okay, and this is the top model of the work. So here this is a top model. We are given as an input clock reset mode, A input, B input, and output we are taken as a multiplication result. Okay, and here once we are given the input A input, B input, it will be come on input preprocessing and input register. Okay, 1, and this is a stage 1 operation, sign processing, exponent comparison, multiplication array, and pipeline 0 register. Okay, and after that the alignment registers, added tree, pipeline 1 register. Okay, and exponent normalizations and mantissa normalizations and output selection method and output register. Okay, here one thing we are do with the proposed method. Okay, here we are used as a 79 down to 0 bits only. We are not used as per the paper of 159 down to 0. Okay, so why? Because that much bit size it's not required. Okay, so why means we are calculated with the Excel sheet. Okay, so this is a Excel sheet work. Okay, here for 64-bit the 79 down to 0, that means 80 bit is enough. Okay, so first one is a sign bit. Okay, for all the multiplication, and exponent bit. Okay, so exponent bit means here maximum size of the bit size is 11, 64-bit multiplication, right? That 64-bit multiplications we are used, maximum size of the exponent value is 11. Okay, that 11 we are used it on here. Okay, exponent size is 11, 78 down to 64. Okay, after that balance is 52 bit. Okay, here, so 63 down to okay, so this much bit is enough. Here 63 down to 11, right? So this is a bit size is enough. Okay, and parallelly we are given some excess of bits. Okay, this excess of bits we are given. Okay, so here the splitted thing is the exponent value and sign bit we are used for one FP16. Okay, why? Because here they are splitted the value with the number of FP16. Okay, you can check it on here. Okay, in the figure 8 they have splitted the value up to number of FP16 and FP32. Okay, so as per that we have splitted the value. The exponent and sign will take a 1 FP16 and this mantissa value will take a 4 FP16 method. Okay, and 32 means FP32 332 we are used. Okay, and F64s we are used. Okay, so based upon that we have developed this work in 79 down to 0, and B also we are plotted. Okay, and we have developed a 12 cross 12 approximate multiplier also with using the base paper compressor. Okay, so here you can check the compressors and full adders and half adders for 12 cross 12 bit multiplication. Okay, and coding part, you can check the input processing, input register, sign processing, exponent comparisons, multiplications array, pipeline 0, alignment register. Okay, and added tree. Okay, and yeah, this is a code for 64 cross 64 segmented multiplication. So this segmented multiplication we are used as a number of 12 bit. Okay, and we are added this bit in as per the base paper. Okay, and this is a simulation result for this multiplication. Okay, so this is a multiplication for 16 bit. Okay, so here 16 bit, this is a code for compressor method. Okay, compressor method means it's a proposed method from the paper. Okay, this is a 16 bit code. Okay, so here error mismatching values it's happen. Why? Because here, right, error will be high, and some of the cases error will be 0. Okay, here you can check the multiplication result and result value, both will be equal, so error will be 0, and this cases error will be high. Okay, so why? Because some of the cases it will showing the error in the mantissa. Okay, why? Because in the paper they are used as a compressor based multiplication. Okay, so compressor means it's a approximate value only, it's not an accurate one, so based upon that it will create as a approximate value. Okay, and in the accurate part of the coding, this is the accurate part of the coding, it will be same for all the thing, but we are not used the paper based approximate multiplier. In this cases you can check the multiplication output. Okay, this is a 16 bit multiplication output, you can check it. Okay, so if you need to run again 1 microsecond, okay, the test will be passed continuously. Okay, okay, and if you change the mode value on here, so here 0 1 1 0 1 1. Okay, so whatever output you can give. Now I'll give in the single precision method. Okay, you can check the value on here. Okay, so this is the output for single precision method. Okay, so here you can check, so this is a 16 bit sequence, and this is a 32 bit sequence, and this is a 64 bit method. Okay, and this is a FP multiplier precision multiplier, and this is the input pre-processing registers and exponent comparisons and multiplication array, alignment shifter, adder tree, exponent normalizer, and mantissa normalizer, and output selection. Okay, after that you can check the synthesis report. So this is a synthesis report for full code. So number of sliced registers, number of LUTs, and number of occupied slices, and number of IO base. Okay, and you can check the delay 16.718 nanoseconds. Okay, and you can check power on here. Okay, so this comparisons we are analyzed with the base paper. Here this base paper they are designed this code at cadence, but we are synthesized this code in FPGA, but almost you can check the values, the input pre-processing, you can check the table 9. Okay, so input pre-processing, multiplier array, exponent comparisons, alignment shifter. Okay, leading 0 anticipations. Okay, so these are all things. Okay, and we take a less number of output, that means less number of values compared to the previous one. Okay, here the power will take 3.315 volt. Okay, and you can check the comparison results here. Okay, so here number of sliced registers, number of LUTs, number of occupied slices, number of bonded IOB, delay and power. We are taken the value for multiplier array and exponent comparisons, adder tree, carry selector for 60 bit. Okay, and overall proposed architecture. Okay, so these are the values we are taken. Okay, and you can check the RTL schematic on here. Okay, so this is the RTL schematic. Okay, so here the input we are given into A input and B input. Okay, so it's given directly to the input pre-processing table. Okay, so this is a block for that. So here they are splitted: controller, exponent A, exponent B, mantissa A, mantissa B. Okay, these all things given into the input register, and input register given the value to exponent A and exponent value given to exponent comparisons. Okay, so this exponent comparison means it's a fully for adder structure. Okay, so here it's having a DO RCA 5-bit, DO RCA 8-bit, DO RCA 12-bit. okay, and exponent difference. Okay, if you open the DO RCA 8-bit means it's designed with the DO RCA 4-bit, that means 4-bit RCA, and this 4-bit RCA it will have a PFA. okay, PFA means it's a parallel full adder. okay, it's having a 2 carry output and 2 carry in output, sorry, input. okay, and you can check the output of the exponent difference. It will given on the register 0, and additional one of the register it will come from the multiplication array. okay, this is a multiplication array. Here you can check the full RTL. It will comes under the approximate multiplication. okay, approximate multiplier means 54 cross 54 multiplier, and approximate multiplier 24 cross 24 multiplier, and 12-bit cross 12-bit multiplier. okay, here major part is 54 cross 54 multiplier. It's a segmented multiplier, right? So it's using number of 12-bit cross 12-bit multiplier. okay, so you can check it. And adder part, this is all the adder part. okay, here we are used, and these are the 12-bit multiplication. okay, so here once you are open this 12-bit multiplication, okay, you will get a number of compressors and half adders, full adders. okay, so this compressor as per the paper we are developed it. okay, so this is the architecture for compressor. okay, 2 XOR gate, sorry, 3 XOR gate and 2 multiplexer. okay, and okay, after this pipelining 0, we are given the value to alignment shifter and adder tree. okay, and pipeline 1 register. okay, and the output of pipeline 1 register given to magnitude normalization and exponent normalization. okay, and finally we are taken the output with the output selection. okay, and output register. okay, and finally we are written a abstract document for this project. Title, base paper abstract, improvement of this project, future idea for enhancement, proposed title and proposed abstract, existing system, disadvantages, proposed system, advantages. okay, and related notes for this project. Finally literature survey and references. okay, thank you.
If you need more video related with VLSI projects implementation, please like and subscribe this channel.